Hello, and welcome to the learning curve. Today's topic is on applying game rating systems to data labeling, and our speaker is Logan Ford, who is an engineering lead on the NLP and Search evaluation team, where he works on applying data science to ensure quality on subjective labeling use cases. Before we begin, just a quick housekeeping note. We'll take some questions at the end of the presentation, but if you have any questions as we go along, please feel free to use the Q&A feature and we'll answer all your questions at the end. And with that, Logan, please go ahead and take it away.
Awesome. Thank you, Yuri. All right. So to start, the agenda for today, we'll just be starting with an intro to Scale AI for those of you who aren't familiar. We'll then get into the challenges of skill assessment, an overview of game rating systems, and then the application of game rating systems for this challenge of skill assessment. And then we'll have time at the end for Q&A. So for an intro to Scale, our mission is to accelerate AI development. And the main viewpoint that we have is that analogous to traditional software development, where most of the behavior is defined in the code itself. Of course, your architectures and systems definitely limit or enable you to enact different behavior, but very substantially, the code is what actually defines how your system behaves. And similarly, in AI, we really see the analogous position here as labeling data. Your models definitely can define your total capacity, your inductive biases, how quickly you may learn. But at the end of the day, what actually defines what the different semantic definitions of different labels may be, or what the different classes actually mean for your machine learning system is by how you label the data. And so this is really where Scale focuses, believing that providing excellent labeling of data will, in the end, enable excellent production systems of AI. And just an overview of some of our products, we do labeling through all sorts of modalities, all the way from 3D sensor fusion to documents, images, videos. And we also have other products such as Scale Nucleus for data curation. If you saw our last tech talk, talking about how we are able to debug some of the semantic failure modes of models through Scale Nucleus. And just to kind of give a sense of a lot of the customers that we work with, just can look at this page here, all the way from AV robotics applications to document processing, menu transcription, and then NLP development, such as the case with OpenAI. And to get started on kind of the pipeline as a whole in terms of how Scale works, we start with our data input from customer, which is usually through our Scale API submission, which leads right into our automation engine. And essentially what this means is our automation engine is what powers efficiency gains through the application of ML, as well as making decisions such as how many people should label this piece of data, who works on what, and then finally figuring out how to accumulate several annotations of the same piece of data for a final answer through consensus. And then in certain cases, we even can, when we are unable to meet high enough consensus, we can, for example, have those low agreement tasks go to an expert human reviewer that we trust more confidently. And then eventually this data goes back to the customer. And so the piece that we'll really be digging into today is how do we determine which humans label our data? And the real piece here to execute well on is how do we assess worker skill? And so one idea that we'll really dig into today is this idea of benchmark tasks for doing this. And the main thinking is that we can augment our data set with tasks that we know the answer to, or a golden data set. And you can kind of think of this almost as a validation set, but rather than for a model, it's for our human labelers and our system as a whole. And a few key qualities that our benchmarks need to have are that they have to be indistinguishable, such that our labelers are not aware that they're taking a benchmark, and such that their behavior does not change in reaction to that. they need to be representative such that our benchmarks are match very closely the task at hand, and that we cover all the cases as necessary to ensure that we actually have a good read on quality of the tasks that they're performing on. And then finally, we need to make sure that these benchmarks have very high accuracy golden answers, because at the end of the day, if we're measuring against a bad answer, clearly we are not going to be able to assess quality very optimistically or very directly. So with benchmark tasks, the main thinking here is that we have the answer to these tasks, and then we can serve them to labelers as a way to measure their performance. And just to kind of highlight a naive approach of utilizing benchmark tasks, you could serve them every so many tasks and then remove workers if they ever got below Y% accuracy on the benchmarks they've taken so far. So just as a visual here, we can kind of have this queue of tasks. As they're doing tasks, they go on to the next, and then every so often they'll have a benchmark replaced, have a benchmark replace a task, and then we can measure the quality on those to get a sense of what their overall quality is on the project at hand. And so just to kind of give an example of where, of the type of task we may be working with, and the type of benchmarks that we could be sending to our taskers, to just kind of ground this in reality a bit more, we did release a blog post and OpenAI's paper on human preferences for different summarizations. So we can look at, for example, a piece of text and then choose which summary is most descriptive of this paragraph or is the most descriptive continuation. So yeah, definitely check out that other blog post where we actually dig into detail on making use of benchmarks for tasker evaluation at very large scale. But this is kind of an example that we could be running with today of a categorization project where benchmarks are very handy for measuring quality. And so what's the issue with this naive approach? For one, not all benchmark tasks are equal. They can range in both the degree of ambiguity as well as difficulty. So some tasks are harder than others, and then others are just not as clear in that there's one answer or there are multiple ways that you can interpret them. Another piece is that we want to be sample efficient so that it takes few benchmarks for us to be reactive, and we in general want to have our workers working on tasks, real data and real tasks as much as possible. So we want to have a reliable way to measure quality very quickly. And also, if we have too few benchmarks, they become easily discovered and gamed. So you can imagine if you and your friends were all labeling on a project and you all happen to see the same few set of tasks, you may quickly realize which ones are benchmarks, and therefore your behavior may change, and they are no longer indistinguishable. So we have to have a large enough set of benchmarks such that it's not obvious what tasks are benchmarks through collaboration. And just by managing a larger set of benchmarks, this comes with its own set of challenges. Okay, so now we'll kind of take a pause on benchmark evaluation for a second, and we'll jump into Glicko, which is a public domain rating system, game rating system that we'll be kind of digging into detail here. And yeah, definitely can be used by just about anyone for things. It's been used in chess, for example, as well as online games for matchmaking and for pinning pinning skill of different players in games. And it was made by Mark Glickman as an improvement to ELO, and he describes it as quasi-Bayesian, and we'll dig into the math a little bit here in a second. And like I said, it's been used in many online games, chess federations, even programming competitions. And one key difference from ELO is that it tracks rating deviation or reliability. So the thinking here is that rather than just having one number of describing what your skill level is, we also actually kind of have a certain amount of confidence in what your rating is, or maybe your rating falls within a range. So we can actually describe your skill level at the moment as a distribution of possibilities, your possible real skills, rather than just a single number. And to kind of illustrate this, so first off, we have these two numbers, the rating R, and then RD, which is the deviation. And so on the right, we can visualize this as these different bell curves. And so in blue, this is the player B. We have them starting at the initialized 1500 skill rating and a very large deviation of 100. So the possible values realistically that they could range from go from 1250 to 1750, compared to our player A, which has a rating of 1600 and then a deviation of 40. So we're much more confident of the range that their skill falls in. And this is mostly a function of how many games they've played, since that once we have more data, we're able to become more confident of their true rating. And to kind of get around this issue of just having two numbers to keep track of, one thing we can do is we can take R minus 2 times RD. So RD is actually just the standard deviation. So we can take, if we say R minus 2 times RD, we know that with 98% confidence, the user has a true rating above this value. So this is kind of a lower bound, just because in general, we want to be fairly pessimistic about people's performance, given that we don't want to, in our case, have people labeling data if they're actually not of very high quality. And so, like I said before, we have this initialization of 1500 for R. We have a RD value of 350 to start. And then Glickman also suggested things such as having the RD be capped from decreasing below 30 to ensure that we stay above a certain level of reactivity, such that if it decreases too low, the possible updates start slimming down more and more. And so we want to make sure that as new data comes in, we can shift our belief in both the rating and the deviation very quickly. And just to kind of outline basically how this all comes together in terms of the update rules and what this actually means as far as how your ratings can change when playing a game. We have this example on these two outcomes for a match on the right here between players A and B, where A is the red player and then B is the blue. And so you'll notice in the player A wins case, player A is expected to win here because they have a much higher rating with lower RD. So we're much more confident that they have a higher rating than B. So them winning is pretty expected. And you'll notice that their rating only increases by 3, while it decreases player B's rating for losing by 19. Contrast that to the graph on the right. When player B wins, they actually shift much more up than they shifted down previously when they lost. And this is because they're the underdog. So winning is actually much higher signal and much more descriptive than them losing a game that they were expected to lose, right? So their rating goes up by 34 and player A's rating goes down twice as much as that it would have gone up had they won. And so this is just one of the key principles with both ELO as well as these other game rating systems such as Glicko, where if you gain more for winning a game that you were expected to lose versus winning a game that you were very much expected to win. And just to kind of describe some of how Glicko itself works, the main thinking is that it uses approximate closed form update rules derived from Glickman's work on statistical models. And it's an online algorithm. And I'll touch on what that means for those who may be unfamiliar. But for one, we can always calculate the probability of game outcomes given the current player state, which is really nice. So previously, we can actually, in that example, when we knew one player was expected to win over the other, we can actually put a probability to that. And as far as the actual update rules, since it's online, all we need is the current state of the R and RD values to calculate both the next as well as the game outcome. to calculate the next R and RD values for both players. And yeah, math is here for those of you who are interested in. For the sake of time, won't dig into too much detail here. But these are overall fairly simple calculations in that it doesn't take too much work to implement this yourself. And it's definitely very quick to compute. And so now that we've kind of gone over Glicko as a whole, we can start talking about how we actually apply this at scale and what this means for us. So to start, unlike with games, either online or board games such as chess, we don't have our players going right up against one another. Our labelers are playing against benchmarks and never directly against one another. But we can actually just kind of replace we can apply the game rating system of Glicko in the same way, except we swap out one side of the equation of a player with benchmarks. And so benchmarks kind of act as players in the context of Glicko. And so what this means is when a tasker is about to do a benchmark, we have ratings and deviations for both the tasker as well as the benchmark. And then we can calculate the probability of the tasker getting the benchmark correct or incorrect for each matchup. And then we can look at the game outcome and see whether we were correct or not, and of course, update our values as we go along. And so just to talk, I guess, going back for 1 second, another key point here is that benchmarks are taken by potentially thousands of taskers, versus taskers are only going to take so many benchmarks. So one property that you end up having is that your benchmarks are much more narrow than the tasker distributions. And so you get pretty clear definitions of the difficulty of different benchmarks, which actually allows us to, over time, update our tasker performances much more quickly. Since we're so confident in one side of the equation, that gives us more information on the tasker performance or tasker skill given the performance on a certain matchup. And so digging into some of the results here with this application, we'll kind of be taking two viewpoints. One is on how well it performs statistically. So there's basically two main metrics that we used for measuring how effective it is. For one, we looked at the predictive power. So given that we can make these matchups and then look at the game outcome and the expected probability of each outcome, we can see if we always take the expected outcome, or if we even just map it with the probability, we can measure our R squared, and we actually got pretty good, given how noisy these outcomes can be. Got a pretty good R squared here of 0.6. And so this shows, and we compared this to very basic rudimentary approaches, such as some linear regressions, as well as other methods. This is actually significantly better than the naive approaches you may take for predicting outcomes. And so we got 0.6 R squared here, which was very promising. And then on the other side, we saw stability, and this allowed us to more directly measure against our current methods. And so we had a Spearman of 0.7 across many different simulations of basically subsampling certain matchups and seeing how our rankings changed depending on which matchups we actually included in our calculations. So using our naive approach, we were only getting a Spearman of about 0.45 between these subsamplings, and then ranking all our labelers in terms of skill. Versus with Glicko, things were much more stable and with a Spearman of 0.7. And this is quite a significant difference. And essentially what this tells us is that through using Glicko, we can be more confident that our answers are closer to the true rating that we would get if we had subsampled a different set of benchmarks rather than the ones we necessarily did in this single case. And then there's also other things that we can do in terms of how we actually action on these results. And so with Glicko, it enables us to do a few different things. For one, we're able to do more intelligent serving. So in the same way that in matchmaking systems, they try to match they match players with players of similar skill level. For our case, we do something a little different where we just want to make sure that overall the benchmarks that we serve over time are fairly consistent and follow from a certain distribution, and we can kind of reduce the variance in that they don't get a bunch of hard benchmarks in a row and a bunch of easy benchmarks in a row. They just get a kind of consistent overall skill level over time. And so this allows us to be more confident in measuring differences in behavior over time from the labelers. And so we can know that if they're always going to be getting a certain number of easy benchmarks and always a certain number of hard benchmarks, that we can see if they, for example, get those easy benchmarks wrong. At any point, we can react very quickly to that because we know their behavior probably dipped and their quality has gone down compared to earlier times. And so that brings us to this idea of a surprise rate, where since we can look at the expected outcome of a matchup between labelers and benchmarks, we can find cases where an outcome that is surprising continually happens. So for example, if labelers are unexpectedly doing much more poorly than our probability outcomes said they would, we can flag this as suspicious and either move these labelers off the project, or at least for a certain amount of time, give them more benchmarks so that we get a more dense sampling of their performance before actioning upon it further. And then on the other side, assuming most benchmarks are of high quality, most benchmarks should not have that high of a surprise rate. So if we do have benchmarks where we have poor labelers doing really well on them a lot of times and good labelers doing more poorly, this can be suspicious in terms of the ambiguity or correctness of these benchmarks. And so we can look into this more deeply to make sure that our whole suite of benchmarks is of as high quality as possible. And so with that, that's the end of our talk today, and definitely open for any questions.
Great, thank you so much, Logan. And we do have a couple of questions here in the Q&A. Just to kick things off, could you explain why benchmark distributions are narrower as compared to labeler distributions?
Yeah, so with more, essentially one of the biggest factors in decreasing the width of the distribution, or the variance in terms of possible outcomes, is how many games they've played or how many matchups that we actually have data on, right? With more data points, we're able to more concretely establish what we believe their true rating to be. So just because in general, we have this asymmetry of a smaller set of benchmarks than the number of taskers, a benchmark gets done very, very many times by tons and tons of different labelers. And so we just have very many more data points compared to how many benchmarks a tasker would take. So in general, the distribution just becomes much more narrow for benchmarks. And then this allows us to actually more quickly get a read on the performance of labelers, since those benchmarks kind of define the scale that we're measuring on.
Great. Next question is, can you explain the update rule for RD values?
Yeah, I am not able to get into super deep mathematics here, but I mean, this is a harmonic mean, right? So in general, yeah, it's going to follow the properties of a harmonic mean, in which it's going to bias towards the lower value of the RD versus D. And over time, that basically means that in the first rounds, you're going to have more aggressive decreases of RD. And then over time, it starts to decrease more slowly, given more samples, which in general makes intuitive sense, in that some of your first games are going to be most informative in kind of decreasing your uncertainty, and over time, it's going to taper off. But if you're interested in the mathematics and even some of the intuition, I would definitely recommend reading Glickman's papers, either the statistical model or the Glicko paper. And a lot of these principles are actually very common across any rating system, including that has some idea of rating uncertainty, which is a fairly common concept.
Great. Next question. Are benchmark and player distributions one-dimensional?
Yeah, so that is one of the main assumptions in this framing. And that's certainly not one that I would say that us at Scale believe is the true case. So for these purposes, for this presentation, that's definitely a simplification we went with, but that is definitely a step that you can take, is that if you can break up the different skills at play for labeling, then you can start to measure those more independently and accumulate those scores at the end to determine whether or not you believe this labeler has met the thresholds to work on said project.
Great. How do you avoid labelers being stuck with too high or too low of a rating?
Yeah, so this comes back to this main concept that Glickman had talked about of having this cap of not decreasing the RD below 30. And so the main concept here is that so long as you remain that there's a certain amount of uncertainty, that gives you the flexibility of updating quickly to new data. So given that, if they did perform poorly for some time, that means that if they start to perform well, they can start to shift their distribution rather quickly. In the same case, if you had someone who's performing really well and then they drop off in quality, you can be fairly reactive to that. There's also other things you can do, like for example, with Glicko 2, they start introducing a time decay. So just over time, if someone hasn't been involved in matches, their RD value starts increasing just because with time, people start losing their skills and we're less certain about their true skill level when they come back to play. So some of those similar concepts can apply with data labeling as well.
Great. How does one deal with exhaustion and ceiling effects in cognitive ability of a worker as they perform more tasks?
Yeah, so this is definitely something just involved with managing a project overall, I would say, kind of beyond the exact scope of maybe what we discussed today. But yeah, certainly you have to be mindful of how much your labelers are working. And you want to also, you can also kind of test things like, for example, how much attention they're paying with basically benchmarks that may measure, you might have fairly easy benchmarks that are just essentially testing whether they're paying attention. And so if you have a set of benchmarks that test for that explicitly, you see that they're not doing super well. And then as you serve more, they continue to not perform well on those. That can be a good indication that you may want to essentially put them on pause for some amount of time so that they can come back to it with fresher eyes and hopefully more rest.
Does inter-rater agreement have any role to play in this analysis?
Yeah, so with kind of going back to the very beginning with this automation engine, you can imagine that when we are doing the consensus of many judgments on the same piece of data, one thing that we can take into large account here is the labeler skill according to these rating systems, for example. And so while inter-rater agreement isn't exactly something that would be applied in terms of how you do these updates to skill rating, it can be applied to determine what is the best judgment or whether you've reached high enough consensus to then feel that you've labeled this piece of data with sufficiently high confidence of whatever label that you did give it. But yeah, I mean, you can certainly think of ways that you may create such a statistical model where you're looking at, you're getting some signal given what everyone else labeled this one piece of data as to start having that change the provided rating of any one labeler involved in that consensus judgment.
Great, thank you. So I realize we are at time, but we do have a couple of more questions here in the chat. So I understand if you need to hop off, thank you very much for joining us. But if you have a couple more minutes, how do you define the deviation in the benchmark? What makes it non-zero?
Yeah, so the deviation starts to decrease quite dramatically just given so many attempts. Yeah, I mean, it's a bit open to interpretation in terms of what you actually define as the what the deviation really means. Really, all we can say objectively is that it's some amount of uncertainty, and so just over time, as you have more labelers working on it, and given their relative ratings, you start to have more confidence that this exact number, given the whole scale of all the labelers that are involved in this system, that this is the true number. But you can, after a certain point, just anchor those benchmark values because you're sufficiently confident in them. But then you do have to worry about things like shift over time in terms of how that may affect the human labelers. But in general, labeling in total is noisy to some degree, and the difficulty of the benchmark can vary person to person. So that those are some of the different viewpoints you might take in terms of what feeds into that uncertainty.
Great. Just final two questions. One, did you think about artificially increasing the variance for taskers who haven't been shown a benchmark in a while? And maybe show them benchmarks when the variance increases above a specific threshold?
Yeah, certainly in terms of this decay over time concept with the deviation, it can both be in terms of how many tasks they've gone since they've gotten a benchmark, as well as, or just in terms of how many benchmarks they've gotten in total in a certain amount of time, as well as actual just time on the clock. So yeah, there's multiple viewpoints you can take there. I think the ideal answer is somewhere in between in terms of how you actually implement that decay. But yes, that's definitely a very good point, and something worth incorporating at least to some extent.
Great. And one last question. Does Glicko have an easy way to handle situations where you discover that a tasker was cheating or a benchmark that had an incorrect answer key?
Yeah, so this surprise rate, as well as looking at just the overall ratings of benchmarks, a lot of times those are good indicators of what you should dig into further. So things with very high surprise rate, or if they are extremely difficult benchmarks, those tend to be ones that you should dig deeper on and do some amount of audits. For cheating, it's a little less obvious, but there are some ways that you can start to tell if there's dramatic changes in their performance, right? If they start getting every benchmark right after previously not doing nearly as well before, things along that line. But I would say in general, in terms of catching cheating, rating systems aren't necessarily the best way to capture that. But yeah, there are different ways that you can start to model some of these variables of basically like your belief of cheating and whatnot with some sort of statistical model.
Great. Thank you, Logan. And thank you all for joining us today.